Hello and welcome. Here's that book that I told that little story about the why I love engineers. I told you I owned this book. Oh, ye of little faith. Riemannian Geometry Beginner's Guide by Frank Morgan. Frank, may I call you Frank? This book's over my head. It's little, but it's intense. After the story about the engineer, it starts out here next with Gaussian curvature. He goes, boom, Laplacian of a function defining Gaussian curvature. Well, I don't know what Gaussian curvature is. So I need to start at the beginning. I think that's a better place to start. So let's get at it. Okay, here we go. If I'm going to understand anything about differential geometry, I got to start at the beginning of differential geometry, which was Gauss, with Gauss. Now, because I've been doing lots of tensor, the calculus, I want to derive this Gaussian curvature in the tensor, the syntax, and later compare it to the Riemannian curvature, the tensor. You don't need tensor, the calculus, to understand the Gaussian, the curvature. You can do it with differentials. That's the way he did it. By the way, did you know that Riemann was a student of Gauss? Bernhard Riemann went to the university to become a Lutheran minister, and he sat in on one of Gauss's lectures. I just read this story this morning. This is great. One of Gauss's lectures, and Gauss was so impressed with him, he convinced him to change to mathematics. So, isn't that wild? I love that stuff. Okay, so this is my goal, and my motivation is I do this under the old adage that if I can't explain it, then that means I don't understand it. And there's no one around here to explain it to. So all I have is you. And that's why I'm doing this. And I appreciate you. All right. So we want to start with what's called an embedded manifold. It's also called a submanifold. Now, here's what we're going to do. We're going to embed a sphere with a constant radius inside of a three-dimensional Cartesian plane, right? So we've got a 2 dimensions embedded within 3 dimensions, and the surface of the sphere, the 2 dimension, is the submanifold, and the Cartesian, the frame we're going to use, is called the ambient. These are the words they use, okay? So the surface of the sphere is the submanifold, and the Cartesian plane is the ambient. Now, you've all seen this before. There's a vector here which has these projections on these planes. You've got all these right angles, so you can define this as a x, y, and a z. So we're going to use these as our parameterization. I also got a frosty beverage here. Forgive me. It's very good. Okay. Now, here's the way I understand this. and jump in on me if I'm wrong. Okay. We can use these, the submanifold, the parameters on this, the surface of the sphere. We're going to call those the surface, the coordinates. So that vector can be a function of the surface, the coordinates. The vector can also be and is a function of the ambient, the coordinates, but the ambient coordinates can also be a function of the surface, the coordinates. So we've got 2 arguments here, okay? So we want to take a differential of this, and because we have 2 arguments, we have to use the chain rule, right? So we're going to differentiate it with respect to the surface, the coordinates. So when you see alpha, it means the submanifold, and when you see a Latin letter, it means the ambient, the space. Apparently, the tensor cops are very picky about this. I did not know that. All right, so we have these 3 items. Now, we know what this is and what this is already, right? So the partial derivative of a vector with respect to a coordinate is a basis vector. So this is the surface, the coordinate basis vector, S alpha. And that one we've been using all along. The partial derivative of the vector with respect to a coordinate in the ambient space is just the regular old covariant, the basis vector that we always use. So in this case, these are just the ijk's, right? These are just these guys, I, J, and K. There's nothing sexy about it at all, okay? So let's look at just some of what we're doing first. All right, so here's our Cartesian plane. We've got just our ijk's on here, right? So this is I hat, j hat, and k hat. Now we're going to define a vector on here, just anywhere, okay? And this vector has this angle here away from the North Pole, which is theta, and it has this angle here in the xy plane, phi. And you can see it move back and forth from the North Pole, right? So that's theta, and here's phi. So it swings around the equator. That's phi. Now what we're going to do is leave the radius the fixed. We're going to call the radius A, and I just set it at 1. You can set it at anything. As long as it's fixed, that's what allows you to work in the coordinates on the surface of the sphere, all right? So now we're going to pop a point on the end of this vector. There he is. Now we're going to put a sphere with that radius, all right? So now this point is on the surface of the sphere, and we can move him around, or her, the same thing, right? So when you're doing Gaussian, the curvature like this is in an embedded manifold, the way I understand it is you're doing it at that point. What is the curvature at that point? Well, that point is equal everywhere on the sphere, right? It's the same curvature everywhere on the sphere. Now, what we can also do is put a plane on that looks like this. Do you see it? It just touches it right at that point. So this is our tangent plane, We're going to need that later. All right, so let's keep rocking. Okay, so we did this differentiation of this compounded argument, for lack of a better word. We've got this basis vector for the surface, the coordinates. We got this basis vector for our regular, the coordinates, which they're calling the ambient, the coordinates, right? So now we want to know, what's this thing here? What is this? The partial derivative of a ambient coordinate with respect to a surface, the coordinate. Well, this is given the name shift tensor. And later on, we'll see why it's shifty, because it's used to shift things. All right. Now, notice here I have a contravariant Latin letter, which is implying this is in the numerator, and a covariant Greek letter, which is implying this is in the denominator. So this is what the tensor cops are very, very picky about. When you have these mixed, the tensors between an embedded manifold and an ambient space, that you keep these right. That's what I read. Okay, so now that we have all these things defined, we can just write this equation, which is the unit vector in the embedded space, the surface, is equal to the basis vector in the ambient space times this new thing called the tensor. Okay, so now we actually can solve for this, but first let's look at it. This notation here. So because this is on the surface, right? Get out of there, dude. Because this is on the surface, there's only 2 coordinates. There's S1 and S2. That's it. You're not going up or down. So this can only be 1 or 2, but this is the normal XYZ plane. So this can be IJK. So we have to write S1 then as 1, 2, 3, or IJK, and that means there's 3 of these. So in total, there's 2 equations, but each one has 3 components. That's what this means. Okay? So the surface, the coordinates S1, S2 are theta and phi. Those are the only variables that we have here, right? We're not varying R, just theta and phi. The ambient, the coordinates are just X, Y, Z, but we're going to parameterize those as what you saw in that drawing up here. Yes? X, Y, and Z. All right? We're rocking now. Okay, now we're going to put that in this equation, and we're going to have a 3 by 2, the matrix. Is it 2 by 3 or 3 by 2? It's 3 by 2, I think. Okay, so we're going to have Z11. Now look at this. The alphas now, there's only 2 of them, right? So there's 1 and 2, 1 and 2, 1 and 2. But the i's, there's 3 of them. 1, 2, 3, 1, 2, 3. IJK, IJK. So now we have to find these partial derivatives. All right. So we plug in our, as an example, this is X. X1 is just X. So we put in the parameter for X. We're going to take the partial derivative with respect to theta, which means this is held constant and that's held constant. So we just get A cosine theta cosine phi. We do the next one, but here we've changed it to a 2. Do you see that? So 2 is phi. So now these are constant, and this is what we're differentiating. So we get a negative A sine theta cosine theta. And so we just keep doing that. Now we change to 2, which is y. That's the y, the variable. With respect to theta, we get this. Y with respect to phi, we get this. Now we go for z. So z with respect to theta, we get this. And z with respect to phi, we get 0 because there's no phi's in here. It's just A cosine theta. So the partial differential of this is a constant. And the derivative of a constant is 0. So now we've got our shift tensor doohickey, which looks like this. All right. Now we can use this to find our surface of the basis vectors because we know everything in this equation. We know this. We just found it. We know what this is. This is just IJK or X hat, Y hat, Z hat, whichever is your favorite, right? So all we have to do here is multiply this column, because look back up here. You see, this is all alpha equals 1. Alpha equals 1. So we multiply that column here times IJK, and we get this. Multiply this column times IJK, and we get this. Okay. Now let's look at this on on the matrix, the calculator. Okay. So we have our. I just made these numbers up. They don't mean nothing. So we have our our Cartesian, the unit vectors. So it would just be IJK, and this is our shift the tensor, right? And this the format. So all we're doing is multiplying this by this. So this is a 3 by 1 and a 3 by 2. So can we multiply those together? No. You big dummy. You cannot multiply matrices with incompatible dimensions. Okay, well, what do we do then? Okay, we have to do the old linear algebra trick. So we have A is a 3 by 1. We transpose it. We get a 1 by 3. So now we have M times N. We can multiply by N times M, which is this, right? So now we're going to do a 1 by 3 times a 3 by 2, and it works. So it gives us a 1 by 2, which is exactly what we have here. There's only 2 of these. All right, so now we've got our basis vectors of the surface. And we can use these guys to find our metric, the tensor of that surface. And you know what the metric, the tensor is. It's just the product of the basis vectors. So we got S1.S1, S1.S2, S2.S1, and S2.S2. All right. So all we have to do is multiply these things out. Now remember, you're dealing here with orthonormal basis vectors. Remember? So I hat dot I hat is 1, but I hat dot j hat is 0. So all of these cross terms, ij, ji, jk, kj, ki, they're all 0. So you don't have to worry about any of those. So you're basically just squaring this thing that looks like a polynomial, right? So we get this expression, a squared is cosine squared theta, cosine squared phi. We square this one, we square this one. Now that's a negative, so a negative and a negative is a positive, right? Now we can factor out some stuff here. As we see here, we have a squared cosine squared the theta, so we'll factor this out first, right? So that gives us this times what we factored this out, leaves us with this, and this piece is left over. Well, you know what that is. That's the identity of 1. Cosine squared theta plus sine squared, phi. This is equal to 1. And that leaves this, and that's equal to 1. So the first component of the metric is a squared. All right, now let's do a cross term. All right, so we take this one, we dot it with this one, the same thing. It's only the i's and the j's and the k's that go together. We get negative a cosine theta, cosine phi, phi theta. See, these are identical. Every piece is in here, so it's just 0. Now, we know that the metric tensor is a symmetric tensor about the diagonal, remember? So what's over here is over here. So that means if we just did this one is 0, so we know that one's 0. We do the last one, which is S22. We do the exact same thing. We just square this. And we get a squared sine squared theta. All right, one more thing we need is here's the metric, the tensor for embedded the surface, the submanifold. Now we want the inverse metric tensor. So this is the covariant metric tensor. We want the contravariant metric tensor, which is the inverse of this matrix. And since this is symmetric about the diagonal and these are 0, it's really easy to invert it, right? I don't have to do anything sexy. I just put these guys, I just invert these guys. All right. So this is just part 1 of a series I'm going to do on this Gaussian, the curvature, and then comparing, the Gaussian curvature tensor, and compare that to the Riemann curvature, the tensor. I don't want these to get too long. I don't like long the videos, so I'm going to break them up into parts. All right, so that's the end of this part, and I'll see you later. Thanks for watching.